Welcome to the I Can't Sleep podcast, where I help you drift off one fact at a time. I'm your host, Benjamin Boster, and today's episode is about sharks. Sharks are a group of elasmobranch cartilaginous fishes characterized by a ribless endoskeleton, dermal denticles, 5 to 7 gill slits on each side, and pectoral fins that are not fused to the head. Modern sharks are classified within the division Selachii and are the sister group to the batomorphi rays and skates. Some sources extend the term shark as an informal category, including extinct members of Chondrichthyes, cartilaginous fish, with a shark-like morphology, such as hybodonts. Shark-like Chondrichthyans, such as Cladoselachii and Doliitis, first appeared in the Devonian period, 419 to 359 million years ago. Though some fossilized Chondrichthian-like scales are as old as the late Ordovician, 458 to 444 million years ago. The earliest confirmed modern sharks, Selachii, are known from the early Jurassic, around 200 million years ago, with the oldest known member being Agelaeus, though records of true sharks may extend back as far as the Permian. Sharks range in size from the small dwarf lantern shark, a deep-sea species that is only 17 centimeters in length, to the whale shark, the largest fish in the world, which reaches approximately 12 meters in length. They are found in all seas and are common in depths up to 2,000 meters. They generally do not live in fresh water, although there are a few known exceptions, such as the bull shark and the river sharks, which can be found in both seawater and freshwater, and the Ganges shark, which lives only in freshwater. Sharks have a covering of placoid scales, denticles, that protects the skin from damage and parasites in addition to improving their fluid dynamics. They have numerous sets of replaceable teeth. Several shark species are apex predators, which are organisms that are at the top of their food chain, with select examples including the bull shark, tiger shark, great white shark, mako sharks, thresher sharks, and hammerhead sharks. Some sharks are filter-feeding planktivores, such as the whale shark and basking shark, which are among the largest fish ever lived. Until the 16th century, sharks were known to mariners as sea dogs. This is still evidential in several species termed dogfish, or the porbeagle. The etymology of the word shark is uncertain. The most likely etymology states that the original sense of the word was that of predator, one who preys on others, from the Dutch schurk, meaning villain, scoundrel, which was later applied to the fish due to its predatory behavior. A now disproven theory is that it derives from the Yucatec Maya word xoch, meaning shark. Evidence for this etymology came from the Oxford English Dictionary, which notes that shark first came into use after Sir John Hawkins' sailors exhibited one in London in 1569, and posted shark to refer to the large sharks of the Caribbean Sea. However, the Middle English Dictionary records an isolated occurrence of the word shark, referring to a sea fish, in a letter written by Thomas Beckington in 1442, which rules out a New World etymology. The oldest total group Chondrichthyans, known as acanthodians or spiny sharks, appeared during the early Silurian, around 439 million years ago. The oldest confirmed members of Elasmobranchii, sensulato, the group containing all cartilaginous fish, more closely related to modern sharks and rays than to chimeras, appeared during the Devonian. Anachronistically, the oldest probable representatives of Euselachii, the group containing modern sharks and rays to the exclusion of most extinct elasmobranch groups, date to the Carboniferous. Selachii and Batomorphi are suggested by some to have diverged during the Triassic. Fossils of the earliest true sharks may have appeared during the Permian, based on remains of Synecodontiforms found in the early Permian of Russia, but if remains of Synecodontiforms from the Permian and Triassic are true sharks, they only had low diversity. Modern shark orders first appeared during the early Jurassic, and during the Jurassic, true sharks underwent great diversification. Sharks largely replaced the hybodonts, which had previously been a dominant group of shark-like fish during the Triassic and early Jurassic. Shark teeth are embedded in the gums rather than directly affixed to the jaw, and are constantly replaced throughout life. Multiple rows of replacement teeth grow in a groove on the inside of the jaw and steadily move forward in comparison to a conveyor belt. Some sharks lose 30,000 or more teeth in their lifetime. In most species, teeth are replaced one at a time, as opposed to the simultaneous replacement of an entire row, which is observed in the cookie cutter shark. Shark skeletons are very different from those of bony fish and terrestrial vertebrates. Sharks and other cartilaginous fish, like skates and rays, have skeletons made of cartilage and connective tissue. Cartilage is flexible and durable, yet is about half the normal density of bone. This reduces the skeleton's weight, saving energy. Because sharks do not have rib cages, they can easily be crushed under their own weight on land. The jaws of sharks, like those of rays and skates, are not attached to the cranium. The jaw's surface, in comparison to the shark's vertebrae and gill arches, needs extra support due to its heavy exposure to physical stress and its need for strength. It has a layer of tiny hexagonal plates called tesserae, which are crystal blocks of calcium salts arranged as a mosaic. This gives these areas much of the same strength found in the bony tissue found in other animals. Generally, sharks have only one layer of tesserae, but the jaws of large specimens such as the bull shark, tiger shark, and the great white shark have 2 to 3 layers or more, depending on body size. The jaws of a large great white shark may have up to 5 layers. In the rostrum, snout, the cartilage can be spongy and flexible to absorb the power of impacts. Fin skeletons are elongated and supported with soft and unsegmented rays, named ceratotrichia, filaments of elastic protein resembling the horny keratin in hair and feathers. Most sharks have 8 fins. Sharks only drift away from objects directly in front of them because their fins do not allow them to move in the tail-first direction. Unlike bony fish, sharks have a complex dermal corset made of flexible collagenous fibers and arranged as a helical network surrounding their body. This works as an outer skeleton, providing attachment for their swimming muscles and thus saving energy. Their dermal teeth give them hydrodynamic advantages as they reduce turbulence when swimming. Some species of shark have pigmented denticles that form complex patterns like spots and stripes. These markings are important for camouflage and help sharks blend in with their environment, as well as making them difficult for prey to detect. For some species, dermal patterning returns to healed denticles even after they have been removed by injury. Tails provide thrust, making speed and acceleration dependent on tail shape. Caudal fin shapes vary considerably between shark species due to their evolution in separate environments. Sharks possess a heterocircle caudal fin in which the dorsal portion is usually noticeably larger than the ventral portion. This is because the shark's vertebral column extends into that dorsal portion, providing a greater surface area for muscle attachment. This allows more efficient locomotion among these negatively buoyant cartilaginous fish. By contrast, most bony fish possess a homocircle caudal fin. Tiger sharks have a large upper lobe, which allows for slow cruising and sudden bursts of speed. The tiger shark must be able to twist and turn in the water easily when hunting to support its varied diet, whereas the porbeagle shark, which hunts schooling fish, such as mackerel and herring, has a large lower lobe to help it keep pace with its fast-swimming prey. Other tail adaptations help sharks catch prey more directly, such as the thresher shark's usage of its powerful elongated upper lobe to stun fish and squid. Unlike bony fish, sharks do not have gas-filled swim bladders for buoyancy. Instead, sharks rely on a large liver filled with oil that contains squalene, and their cartilage, which is about half the normal density of bone. Their liver constitutes up to 30% of their total body mass. The liver's effectiveness is limited, so sharks employ dynamic lift to maintain depth while swimming. Sand tiger sharks store air in their stomachs, using it as a form of swim bladder. Bottom-dwelling sharks, like the nurse shark, have negative buoyancy, allowing them to rest on the ocean floor. Some sharks, if inverted or stroked on the nose, enter a natural state of tonic immobility. Researchers use this condition to handle sharks safely. Like other fish, sharks extract oxygen from seawater as it passes over their gills. Unlike other fish, shark gill slits are not covered, but lie in a row behind the head. A modified slit called a spiracle lies just behind the eyes, which assists the shark with taking in water during respiration and plays a major role in bottom-dwelling sharks. Spiracles are reduced or missing in active pelagic sharks. While the shark is moving, water passes through the mouth and over the gills in a process known as ram ventilation. While at rest, most sharks pump water over their gills to ensure a constant supply of oxygenated water. A small number of species have lost the ability to pump water through their gills and must swim without rest. These species are obligate ram ventilators and would presumably asphyxiate if unable to move. Obligate ram ventilation is also true of some pelagic bony fish species. The respiratory and circulatory process begins when deoxygenated venous blood travels to the shark's two-chambered heart. Here, the shark pumps blood to its gills via the ventral aorta, where it branches into afferent bronchial arteries. Gas exchange takes place in the gills, and the reoxygenated blood flows into the efferent bronchial arteries, which come together to form the dorsal aorta. The blood flows from the dorsal aorta throughout the body. The deoxygenated blood from the body then flows through the posterior cardinal veins and enters the posterior cardinal sinuses. From there, venous blood re-enters the heart ventricle and the cycle repeats. Most sharks are cold-blooded, or more precisely, poikilothermic, meaning that their internal body temperature matches that of their ambient environment. Members of the family Lamnidae, such as the short-fin mako shark and the great white shark, are homeothermic and maintain a higher body temperature than the surrounding water. In these sharks, a strip of aerobic red muscle located near the center of the body generates the heat, which the body retains via a countercurrent exchange mechanism by a system of blood vessels called the rete mirabili, miraculous net. The common thresher and big-eye thresher sharks have a similar mechanism for maintaining an elevated body temperature. Larger species like the whale shark are able to conserve their body heat through sheer size when they dive to colder depths. The scalloped hammerhead closes its mouth and gills when diving to depths of around 800 meters, holding its breath until it reaches warmer waters again. In contrast to bony fish, with the exception of the coelacanths, the blood and other tissue of sharks and chondrichthyes is generally isotonic to their marine environments because of the high concentration of urea, up to 2.5%, and trimethylamine N oxide, TMAO, allowing them to be in osmotic balance with the seawater. This adaptation prevents most sharks from surviving in freshwater, and they are therefore confined to marine environments. A few exceptions exist, such as the bull shark, which has developed a way to change its kidney function to excrete large amounts of urea. When a shark dies, the urea is broken down to ammonia by bacteria, causing the dead body to gradually smell strongly of ammonia. Research in 1930 by Homer W. Smith showed that sharks' urine does not contain sufficient sodium to avoid hypernatremia, and it was postulated that there must be an additional mechanism for salt secretion. In 1960, it was discovered at the Mount Desert Island Biological Laboratory in Salisbury Cove, Maine, that sharks have a type of salt gland located at the end of the intestine, known as the rectal gland, whose function is the secretion of chlorides. A few sharks appear fluorescent under blue light, such as the swell shark and the chain cat shark, where the fluorophore derives from a metabolite of kynurenic acid. Sharks have keen olfactory senses located in the short duct, which is not fused, unlike bony fish, between the anterior and posterior nasal openings, with some species able to detect as little as 1 part per million of blood in seawater. The size of the olfactory bulb varies across different shark species, with size dependent on how much a given species relies on smell or vision to find their prey. In environments with low visibility, shark species generally have larger olfactory bulbs. In reefs where visibility is high, species of sharks from the family Carcharinidae have smaller olfactory bulbs. Sharks found in deep waters also have large olfactory bulbs. Sharks have the ability to determine the direction of a given scent based on the timing of scent detection in each nostril. This is similar to the method mammals use to determine direction of sound. Shark eyes are similar to the eyes of other vertebrates, including similar lenses, corneas, and retinas, though their eyesight is well adapted to the marine environment with the help of a tissue called tapetum lucidum. The tissue is behind the retina and reflects light back to it, thereby increasing visibility in the dark waters. The effectiveness of the tissue varies, with some sharks having stronger nocturnal adaptations. Many sharks can contract and dilate their pupils like humans, something no teleost fish can do. Sharks have eyelids, but they do not blink because the surrounding water cleans their eyes. To protect their eyes, some species have nictitating membranes. This membrane covers the eyes while hunting and when the shark is being attacked. However, some species, including the great white shark, do not have this membrane, but instead roll their eyes backwards to protect them when striking prey. The importance of sight in shark hunting behavior is debated. Some believe that electro and chemoreception are more significant, while others point to the nictitating membrane as evidence that sight is important, since presumably the shark would not protect its eyes were they unimportant. The use of sight probably varies with species and water conditions. The shark's field of vision can swap between monocular and stereoscopic at any time. A microspectrophotometry study of 17 species of sharks found 10 had rod photoreceptors and no cone cells in their retinas, giving them good night vision while making them colorblind. The remaining 7 species had, in addition to rods, a single type of cone receptor sensitive to green, and seeing only in shades of gray and green are believed to be effectively colorblind. The study indicates that an object's contrast against the background, rather than color, may be more important for object detection. Although it is hard to test the hearing of sharks, they may have a sharp sense of hearing and can possibly hear prey from many miles away. The hearing sensitivity for most shark species lies between 20 and 1,000 hertz. A small opening on each side of their heads, not the spiracle, leads directly to the inner ear through a thin channel. The lateral line shows a similar arrangement and is open to the environment via a series of openings called lateral line pores. This is a reminder of the common origin of these two vibration and sound detecting organs that are grouped together as the acoustico-lateralis system. In bony fish and tetrapods, the external opening into the inner ear has been lost. The ampullae of Lorenzini are the electroreceptor organs. They number in the hundreds to thousands. Sharks use the ampullae of Lorenzini to detect the electromagnetic fields that all living things produce. This helps sharks, particularly the hammerhead shark, find prey. The shark has the greatest electrical sensitivity of any animal. Sharks find prey hidden in sand by detecting the electric fields they produce. Ocean currents moving in the magnetic field of the earth also generate electric fields that sharks can use for orientation and possibly navigation. The lateral line system is found in most fish, including sharks. It is a tactile sensory system which allows the organism to detect water speed and pressure changes nearby. The main component of the system is the neuromast, a cell similar to hair cells present in the vertebrate ear that interact with the surrounding aquatic environment. This helps sharks distinguish between the currents around them, obstacles off on their periphery, and struggling prey out of visual view. The shark can sense frequencies in range of 25 to 50 hertz. Shark lifespans vary by species. Most live 20 to 30 years. The spiny dogfish has one of the longest lifespans at more than 100 years. Whale sharks may also live over 100 years. Earlier estimates suggested that the Greenland shark could reach about 200 years. But a recent study found that a 5.02 meter long specimen was 392 plus or minus 120 years old, i.e., at least 272 years old, making it the longest lived vertebrate known. The classic view describes a solitary hunter ranging the oceans in search of food. However, this applies to only a few species. Most live far more social, sedentary, benthic lives, and appear likely to have their own distinct personalities. Even solitary sharks meet for breeding or at rich hunting grounds, which may lead them to cover thousands of miles in a year. Shark migration patterns may be even more complex than in birds, with many sharks covering entire ocean basins. Sharks can be highly social, remaining in large schools. Sometimes more than 100 scalloped hammerheads congregate around seamounts and islands, e.g. in the Gulf of California. Cross-species social hierarchies exist. For example, oceanic white-tip sharks dominate silky sharks of comparable size during feeding. When approached too closely, some sharks perform a threat display. This usually consists of exaggerated swimming movements and can vary in intensity according to the threat level. In general, sharks swim or cruise at an average speed of 8 kilometers per hour. But when feeding or attacking, the average shark can reach speeds upwards of 19 kilometers per hour. The short-fin mako shark, the fastest shark, and one of the fastest fish, can burst at speeds up to 50 kilometers per hour. The great white shark is also capable of speed bursts. These exceptions may be due to the warm-blooded or homeothermic nature of these sharks' physiology. Sharks can travel 70 to 80 kilometers in a day. Sharks possess brain-to-body mass ratios that are similar to mammals and birds, and have exhibited apparent curiosity and behavior resembling play in the wild. There is evidence that juvenile lemon sharks can use observational learning in their investigation of novel objects in their environment. All sharks need to keep water flowing over their gills in order for them to breathe. However, not all species need to be moving to do this. Those that are able to breathe while not swimming do so by using their spiracles to force water over their gills, thereby allowing them to extract oxygen from the water. It has been recorded that their eyes remain open while in this state and actively follow the movements of divers swimming around them, and as such, they are not truly asleep. Species that do need to swim continuously to breathe go through a process known as sleep swimming, in which the shark is essentially unconscious. It is known from experiments conducted on the spiny dogfish that its spinal cord, rather than its brain, coordinates swimming, so spiny dogfish can continue to swim while sleeping. And this also may be the case in larger shark species. In 2016, a great white shark was captured on video for the first time in a state researchers believed was sleep swimming. Sharks are found in all seas. They generally do not live in freshwater, with a few exceptions, such as the bull shark and the river shark, which can swim both in seawater and freshwater. Sharks are common down to depths of 2,000 meters, and some live even deeper, but they are almost entirely absent below 3,000 meters. The deepest confirmed report of a shark is a Portuguese dogfish at 3,700 meters. Sharks figure prominently in Hawaiian mythology. Stories tell of men with shark jaws on their back who could change between shark and human form. A common theme was that a shark man would warn beachgoers of sharks in the waters. Hawaiian mythology also includes many shark gods. Among a fishing people, the most popular of all aumakua, or defied ancestor guardians, are shark aumakua. Kamaku describes in detail how to offer a corpse to become a shark. The body transforms gradually until the kahuna can point the awestruck family to the markings on the shark's body that correspond to the clothing in which the beloved's body had been wrapped. Such a shark aumakua becomes a family pet, receiving food and driving fish into the family net and warding off danger. Like all aumakua, it had evil uses, such as helping kill enemies. The ruling chief typically forbade such sorcery. Many native Hawaiian families claim such an aumakua, who is known by name to the whole community. Kamoho'ali'i is the best known and revered of the shark gods. He was the older and favored brother of Pele, and helped and journeyed with her to Hawaii. He was able to assume all human and fish forms. A summit cliff on the crater of Kilauea is one of his most sacred spots. At one point, he had a heiau, temple or shrine, dedicated to him on every piece of land that jutted into the ocean on the island of Molokai. On the island of Tutuila in American Samoa, a U.S. territory, there is a location called Turtle and Shark, Lame Mamalie, which is important in Samoan culture. The location is the site of a legend called Ole Tala Ile Lame Male Malie, in which two humans are said to have transformed into a turtle and a shark. According to the U.S. National Park Service, villagers from nearby Vaitogi continue to reenact an important aspect of the legend at Turtle and Shark by performing a ritual song intended to summon the legendary animals to the ocean's surface, and visitors are frequently amazed to see one or both of these creatures emerge from the sea in apparent response to this call. A popular myth is that sharks are immune to disease and cancer, but this is not scientifically supported. Sharks have been known to get cancer. Both diseases and parasites affect sharks. The evidence that sharks are at least resistant to cancer and disease is mostly anecdotal, and there have been few, if any, scientific or statistical studies that show sharks to have heightened immunity to disease. Other apparently false claims are that fins prevent cancer and treat osteoarthritis. No scientific proof supports these claims. At least one study has shown shark cartilage of no value in cancer treatment.